Greetings to you. Let us continue our discussion on the water parameters, especially drinking water parameters using spectrophotometry. I already covered about 18 parameters which include anions and cations, and today I am talking about the other parameters, that is total hardness. Now you may wonder what is this hardness, total hardness to do with spectrophotometry. Usually total hardness of water is caused by the presence of calcium and magnesium salts, and the solubility of calcium and magnesium salts are quite good, and the presence of these salts leads to the presence of these salts causes the water to taste very hard. You do not feel like drinking it, and then when you want to wash the clothes, it will keep on taking the soap, but it will not produce any lather. As you know, lather production is an essential characteristic whenever you want to wash your clothes. Basically lather is a type of a foam with very large surface area, and whenever we want to wash the clothes with the soap, the lather will catch the particles, dust particles and other things, and then the clothes will get whiter or get cleaner. So hardness has got another property, that is it cannot be used in several industrial processes such as cooling and heating, because as the water evaporates, the soluble salts will precipitate and coat onto the inside of the cooling tubes, which are made of copper or iron, and presence of a little bit of silica will produce calcium silicate and magnesium silicates. Both these salts are essentially like cement, because cement is also a silicate, and as you know, cement buildings etc. last for hundreds of years, and so the silicate salts also will last for several years unless you remove them mechanically. The presence of silicates on the inside of the heat exchanger tubes causes low temperature movement, that is low temperature transfer, and that causes the requirement to increase, the heat requirement will increase. So from industrial point of view also, presence of hardness causing chemicals like calcium and magnesium are not desirable. Hardness of water is measured as ppm, parts per million, of calcium carbonate, because magnesium carbonate and several other carbonates and sulfates also cause hardness, but for easy standard, the Bureau of Indian Standard BIS prescribes a limit of about 300 ppm as calcium carbonate. When no suitable alternate source of water is available, the limit may be relaxed up to 600 ppm, but this works only for drinking water. So usually hardness is determined by titration with ethylene diamine tetraestic acid as a titration method, but we are not recommending that. What we want to recommend here is the Kalmegite method. So in this method, both calcium and magnesium react with this reagent at about pH 12.5 to form a color complex that changes the color of the solution from blue to red blue. The change in the absorbance at 520 nanometers is related to the hardness of water. So, this is the structure of Calmagite. You can see here it contains 3 benzene rings connected with an azo group and OH group. There is one SO3 group. This SO3 group helps in solubilizing the salts. So, we do not need to add any surfactant or something like that, and this azo group and this OH group will help form a complex of ring closure using calcium and magnesium here. So, it is basically a question of ring closure reaction, and the chromophore will increase. The increased chromophore will shift the lambda max to the bathochromic side, that is on the higher wavelength side. So, Calmagite is also colored, but the complex will be more colored with a lambda max slightly towards the right, that is at longer wavelength. So, the reagents include very simple things. Now, I will not go into very much detail about how to prepare the reagents, because all the numbers are given here. So, you have to take concentrated HCl and dilute it to 100 ml, and you can prepare the calcium solution by you have to dry the calcium carbonate, because usually calcium carbonate is associated with water, and you have to remove this water, and that happens around 105 degrees centigrade. You just have to weigh out calcium carbonate into a 100 ml beaker, add 2 normal HCl hydrochloric acid, slowly with swirling till the white powder just dissolves, shake well, remove and transfer the quantity to 100 ml volumetric flask and dilute it to 100 ml. So, that is the standard calcium solution. Now, you can also prepare magnesium solution also, containing 0.2465 gram of magnesium sulfate heptahydrate, that is 7H2O, in deionized water, and make it to 100 ml. For our working reagent, we just mix both calcium and magnesium, prepare 100 ppm equivalent of calcium, because sometimes magnesium may be there, sometimes calcium may be there. So, when we mix equal volumes of calcium and magnesium solutions, we get about 100 ppm of both, but only as the same concentration. Now, since the reaction occurs around pH 12, we need potassium hydroxide solution, and this stock solution is prepared by dissolving potassium hydroxide in deionized water and make up to 100 ml. This potassium hydroxide or any other hydroxide, as I have been repeatedly telling you, we need to dissolve in water, but store in polyethylene bottle with a screw cap. Normally, if you store it in glass bottles, there is a tendency that water will evaporate and it will form it will be very difficult to remove the bottle, to open the bottle. It is a practical difficulty. So, potassium hydroxide working solution also we can prepare by adjusting the pH to 12.5, and we have to prepare 0.015 normal potassium hydroxide. For this, we have to dilute 1 ml of potassium hydroxide stock solution to 100 ml. So, all these things you can calculate yourself, but I am giving you the details because I want to give you a ready-made method, because sometimes it takes time for you. Whenever there is an urgent need for preparation of the reagents, you need a ready reference method to work. So, I am straight away taking you with this introduction, I am straight away taking you to the determination, to the experimental level itself. So, Calmagite reagent also you can prepare by dissolving 0.0725 gram of Calmagite in 100 ml deionized water, but this reagent is available in the market. So, there is no difficulty in obtaining this Calmagite solution. Now, the hardness of a given solution always we measure in about 50 hundreds etc. That is, if you take any river water nowadays in India, you will come across waters having about 100 to 200 ppm of hardness even in river water. In borewell it may go up to it depends upon the depth at which borewell water is extracted, and there also the range may vary from a few hundreds to 1500 ppm. So, basically the range should vary from 50 to 500 range. If we can make a calibration curve using this kind of standard, I think we should be in the business. So, what you should do is we normally do not worry about plus or minus 10% error in measuring the hardness of water. So, we prepare 50, 100, 150, 200 and 250 microliter of 100 ppm standard solution, that is both containing both calcium and magnesium, and then you dissolve them, put them in a volumetric flask, add 1 ml of the reagent, dilute by potassium hydroxide solution and measure. You just have to measure the absorbance after adding 1 ml of 0.015 molar potassium hydroxide solution. You just have to dilute it and measure the absorbance at a wavelength of 520 nanometer against the blank. This tells us that the reagent could be somewhat bluish in color, reddish red violet is the right color, and as usual you have to prepare a calibration curve of the absorbance versus hardness of the water and determine the hardness of the sample by referring the absorbance of the sample to the calibration curve. So, recommended sample volume is about 1 ml, but this refers to only the standard solution. That is, if you take 50 ml 50 micrograms, it gives you that is about 5 ppm. 50 micrograms in 10 ml, that is 5 ppm, it gives you an absorbance of about 0.524 plus or minus 0.01, that is quite good absorbance. And if you get this absorbance with your standard reagents, you are in business. That means all your preparation, standard solutions and other things are all well under good control. So, I am showing you the absorbance of this calcium magnesium, that is complex, that is cal-mag-ite complex, calcium magnesium complex, and then the lambda max, as you can see here, is somewhere around 485. This is around 510 to 520. The curve is somewhat flat here. In this region, not much absorbance range, and so you can be comfortable even if you are plus or minus 5 nanometers this side, that no serious error will be introduced during the measurement. So, this is the calibration curve. You can see that the calibration curve is linear. We have done it up to 120 micrograms here, but you can see that we are already very near the end of the absorbance scale, that is almost 1.2 to 1.5 as dictated by the relative standard error. We should be within 0.2 to 0.8 and that range, and here even around 120 ppm we have absorbance of about 1.3. So, any standard it follows a very nice linear curve. The least square fit value of R square is 0.998. That means the method is quite reliable at this thing, and of course, you will always be having some amount of in normal circumstances you will be having the hardness not within 50 or 100, but you will your range will may be between 200, 300, 500, 600, 800 to 1500. So, what you should do is you do a pilot trial with 1 ml of the given sample. Your calibration curve is done anyway, but the actual sample analysis, if you want to determine the hardness of the sample, you try it with 1 ml. If the absorbance is too high, then you will have to dilute it accordingly, and then try to bring it within 0.2 and 0.8 and multiply it by the dilution factor, and you will be able to determine the hardness of water. A very simple experiment which can be conducted and completed within half an hour if you have all the reagents, and the reagents are all available across the shelf. You will not have any worry regarding this analysis of hardness. So, now I would like to take you to the determination of zinc. Zinc is an essential element of the plants and animals, but at elevated levels it is toxic to aquatic life as well as human life, but that is a very standard statement. Any chemical that is in excess is toxic, that is a fundamental rule. So, but zinc is an essential micronutrient. If you look at some of the soil as well as water samples all over the world, you will see that most of the soils and water, they do contain certain amount of zinc, and that is how it is distributed. It is a widely distributed element. The Bureau of Indian Standards prescribes a limit of 5 ppm, that is relaxable if no suitable alternative source is available, then it is up to 15 ppm. Now, zinc is an industrial element also. It is used for the determination, it is used for anodizing. So, you can see that many of the material around you, that is zinc sheets, as you might have heard, they are all aluminum and iron which are galvanized. So, in galvanization zinc is coated electrolytically. So, the zinc is acts as a sacrificial cathode, protecting the metal inside the zinc coat, and it is also an alloying element. Brass is known, a well known example of copper and zinc alloy. So, brass has got a very bright yellow structure color, and it is also used, and zinc is also used in imparting strength to fibers, especially this cellulose fibers. If you want to make cloth or something like that using viscose or rayon or something like that, then the wood pulp is treated with sodium hydroxide and then dissolved in sodium hydroxide, and then treated with carbon disulfide to remove the lignin, and once the lignin is removed, the fiber becomes white, and this fiber is dissolved in carbon disulfide or and then passed through a spinneret containing number of fibers, and the spinneret is treated with zinc to give strength to the yarn. So, this kind of yarn is is suitable to give strength to the yarn. So, most of the tires of cars, aeroplanes, cycles to etc., and clothes what we wear, viscose clothes, that is very soft materials. They are all made of viscose rayon, which is strengthened with zinc. There are of course several other kinds of industrial applications for zinc. So it is a widely distributed element as well as widely used element. So there is no escape from zinc in your day to day life from this because of the origin, because of the use of zinc in several industrial applications that we normally come across. So the BIS standard prescribes limit of 5 ppm, and this is zinc is determined by using a reagent called as zincon. This zincon is a very special organic compound, and it is a trade name of course, and I am not going to give you the actual chemical name because it will run into about 2 pages, 2 lines, not 2 pages. And but I can tell you that essentially it contains SO3 group here in this end that helps solubilization. There is NN double bond and OH group, NNH grouping, and then OH group is there. There is one ketone group and 3 benzene rings are there. So because of this, there will be complexation of zinc, something like inner complex, and let us see how the reagent works. Basically what happens is, with this kind of structure you can expect several types of metals to complex with zincon. So the trick is there any way that we release zinc from the complex, leaving others in the solution. So that trick has been employed here, that is why I have chosen zinc also to give you in this presentation. So many other metals including zinc form this, but then we add cyclohexanone to this to release the zinc, and then we monitor the absorbance. So the reagents, the reaction is carried out around pH 9 using sodium hydroxide and boric acid, and then zincon reagent is again dissolved in methanol, because obviously many such compounds having high molecular weight, they do not dissolve in water. So you have to have methanol or ethanol which are miscible with water, because we want to develop aqueous methods. So the only we know very few organic chemicals which are miscible with water. So zincon is dissolved in methanol, and methanol is miscible with water, methanol and ethanol. Among the two, methanol is cheaper compared to ethanol. So similarly you can use acetone also, but the rate of evaporation of acetone is much higher than methanol. So the concentration keeps on changing even if you keep it at room temperature. So we normally recommend dissolution in methanol. So that is how we prepare that, and then standard zinc solution we know how to prepare. These are the numbers 0.4398, and sodium ascorbate we have to prepare. They are using ascorbic acid and adding 5 gram of sodium bicarbonate, mixing well, this becomes a slightly darker solution, and the complexing agent is potassium cyanide. So the potassium cyanide is a dangerous chemical, but still there are certain situations in the life of any chemist where he cannot avoid the contact with some of these chemicals which are deadly. Of course, there are other ways of doing zinc analysis, but potassium cyanide is not very unusual. Lot of laboratories do have it, but you may also be able to get it for laboratory purpose. The method of by laboratory method, you should be able to determine the zinc, and Zincon is as I have told you, it is easy to prepare. Working solution, we need 10 ppm, that is 10 microgram. So, see 1000 ppm we need, we are preparing, and then working solution is 10 ppm. So, that is a very simple calculation, and the procedure involves transferring 0 to 50 microgram of zinc, 10 ppm zinc solution, that is up to 5 ml. 10 ppm into 5 would be the 50 micrograms, and 10 divided by 10 ml is 5 ppm. So, 0 to 5 ppm is our working range, and you can add 1 ml of sodium ascorbate solution and buffer solution, followed by 0.5 ml of potassium cyanide. So, you can also add 1 ml of zincon solution, and after adding zincon solution you have to add 0.2 ml of cyclohexanone. This releases the zinc complex from the cyanide, and that mixes it with zincon. So, you allow it to stand for about 30 minutes at room temperature. So, color develops, and you have to measure the absorbance at 620 nanometers. Further chemistry of this reaction you can study in Fiegel, that is a book I have recommended for almost all spectrophotometric procedures. You can also look up third edition of E.B. Sandel, Calorimetric Methods of Analysis. So, sample recommended volume is about 1 ml, and cookbook value would be for 10 micrograms in 10 ml, that is 1 ppm, should give you an absorbance of about 0.34 plus or minus 0.01, that is 0.32 to 0.36, 0.33 to 0.35 absorbance. That should give you fairly good control over the experiment if all your reagents are good. So, this is the lambda max of the spectrum of the spectrum of zincon complex, and this I have recommended 620 nanometer. So, if we go back to this spectrum, you can see that lambda max is around 620 or 630. At the lambda max, the peak is fairly broad. That means again the importance of this situation is plus or minus 2-3 nanometers, plus or that gives you a 5 nanometer range where the absorbance will be almost constant with respect to the zinc concentration, around 620. So, whether you are around 625 or 630, it does not matter, that will give you permission to work with colorimetric methods, that is colorimeters instead of spectrophotometers. So, you can determine zinc in all your samples. It is an agriculturally important element also, because it is a micronutrient. It is also used in pharmaceuticals industries, and then it is very easy to determine zinc around this region. Here at the back, as you look at this curve, you can see that there is lot of, we usually add excess of the reagent, and that reagent compared to when you measure at the blank, you will get a negative value also. So, it is not very unusual, but we concentrate on the absorbance difference, that is positive. So, we can determine this. You can even use this somewhere around 480, that is the negative value, that is the amount of zinc that is liberated. This also you can use as a negative parameter, but it is normally comfortable to use the positive difference between the blank and sample. Now, I would like to tell you about the interference of this method. So, the interference studies we have conducted earlier, and by determining 10 ppm standard, that is how we do. We take 10 ppm or solution in 10 ml, that is 1 ppm, we normally go for 1000 ppm. So, for 1000 ppm we add the interfering species and then measure the absorbance. So, if there is more than 10% of the absorbance, we conclude that it is a interfering element. We did not find any interference from cobalt, nickel, calcium, magnesium, sulphate, phosphate, nitrate, and then silver, fluoride, chloride, iodide, mercury, tartaric acid, citric acid, and surfactants. So, this shows that the method is very robust, and some interference can be overcome by the addition of citrate and tartrate, because around pH 12 we will get only citrate as sodium citrate and sodium tartrate, and 100 microgram of chromium, molybdenum, lead, antimony, arsenic and triton X100. This is a standard surfactant we normally come across. So, in the rivers etc., whenever we use one of the surfactants which I have been telling you, and these things did not interfere up to 100 micrograms levels, that is 1 ppm of zinc and 100 microgram of the interfering element or anion or complex or whatever it is. But aluminum, iron, copper and cadmium, they did not interfere up to 5 times. That is, when you want to determine zinc in 1 ppm, up to 5 ppm of any of these elements will not interfere, and vanadium limit is a little lower, that is up to 2 ppm it can be tolerated, and EDTA and manganese did not interfere. That means, if EDTA does not interfere, you can always conclude that the method will be robust, because EDTA is a very strong complexing agent with several metals that are normally present in drinking water, river water, lake water, pond water and all those things. So, we will continue our discussion in the next class. Thank you.